How do you teach a computer to see? I mean, really see. It wasn't some single aha moment, nope. It was more like a rapid-fire series of incredible breakthroughs that took AI from basically being blind to having vision that, honestly, sometimes rivals our own. Today, we're going to walk through the key landmarks on that journey, the big ideas that really changed everything.
To really get why this matters, let's start with a problem that affects, well, all of us, our food supply. What you're looking at are pictures of rice leaves, a staple food for billions of people. But these leaves are sick. They've got different diseases, bacterial blight, blast disease, brown spot. Now, to you and me, they might look kind of similar. But for a farmer, telling them apart fast, that can be the difference between a healthy harvest and a total disaster.
So this is the core question, right? You can't just program a computer with rules like, if you see a brown spot, it's this disease. It's way too complicated. The lighting changes, the leaf shapes are different, the symptoms vary, it's almost infinite. So how in the world do you teach a machine to see the super subtle patterns that tell one disease from another?
Well, the first part of the answer comes from a technology that's actually inspired by the way our own brains are wired.
The answer is something called a convolutional neural network, or a CNN for short. And here's the absolute key. You don't program it with rules. You train it. You show it thousands, maybe millions of examples, and it just learns. It figures out on its own how to spot the right textures, the right shapes, the patterns that matter. It literally learns by seeing.
So for a while, researchers were making some pretty good progress with this. But then, in 2014, a new design came along that was just a massive leap forward, and it was called VGGNet.
Okay, so here's the big innovation. The older models, like the famous AlexNet that really kicked this whole thing off, they used a few large, complex filters to find patterns. Think of it like trying to build a watch with one big, clumsy wrench. That's the old way. The VGG team thought, wait a minute, what if we do the opposite? What if we use tons of tiny, super simple filters, like a whole set of small, specialized tools, and just stack them one after another in really deep layers? Each tiny filter is only looking for one basic thing, like a diagonal line or a little speck of color. The real magic happens when you stack them up.
And when I say stacked, I mean stacked. This diagram shows the VGG19 architecture. Now don't worry about all the numbers and boxes. Just look at the flow from left to right. An image goes in on the left, and then it goes on this journey through 19 different layers of processing. At the beginning, the layers might just spot simple edges and colors. Then the middle layers combine those to see textures and patterns. And by the end, the final layers have learned to recognize whole parts of the leaf, until the network can say with confidence, yep, that's brown spot.
The creators of VGGNet pretty much summed it up perfectly. Their big insight, the thing that would guide the entire field from then on, was this. A deep and narrow network built from simple parts is way more powerful than a shallow and wide one with complex parts. The new rule was simple. Depth is king.
So how does this abstract idea solve our real-world problem with the rice leaves? Well, to teach VGG19 how to do it, researchers followed this exact recipe. They got thousands of images, they cleaned them up, they even created more training data by flipping and rotating the existing images, and then they fed the whole thing into the VGG19 model and basically said, okay, go learn.
And the result? It was incredible. The VGG19 model, this deep stack of simple little filters, was able to tell the diseases apart with over 90% accuracy. It was a huge success, and it proved that this new philosophy, this focus on depth, was absolutely the right way to go.
So if deep is the key, the answer's obvious, right? Just keep adding more layers. Let's make the models deeper and deeper and deeper. Well, as researchers very quickly found out, it wasn't quite that simple. They hit a wall. A really weird, counterintuitive wall called the degradation problem. When they tried to build a network with, say, 56 layers, it actually performed worse than a network with only 20 layers. What was happening was that the learning signal, the information that helps the network adjust itself during training, was getting weaker and weaker as it traveled backwards through all those layers. By the time it got to the early layers, it had pretty much disappeared. The network was just too deep to learn properly.
This was a total mystery. It just didn't make sense. You're giving the model more layers, more capacity to learn, but the learning signal itself is getting lost in the process. Why would adding more horsepower to the engine actually make it weaker?
The answer came in 2015 from researchers at Microsoft. Their new architecture was called ResNet, and their solution was just beautiful. It was so elegant and so powerful.
They introduced this one simple idea called a skip connection. Think of it like an express lane on a highway. Remember how that learning signal was getting lost as it traveled back through all those layers? Well, a skip connection creates a shortcut. It allows the clean, original information from an earlier layer to completely bypass a few layers and get added back in further down the line. It gives the signal a direct, fresh path so it doesn't get distorted.
This one little idea wasn't just some small improvement, it was a total game changer. It basically solved the degradation problem overnight. All of a sudden, researchers weren't stuck with 20 or 30 layers. They could build networks that were hundreds, even thousands of layers deep. And they actually worked better. This little shortcut was the key that unlocked the true power of deep, deep learning.
So, we've seen VGGNet prove that depth is powerful, and then ResNet came along with the key to unlock even crazier depths. So why is this little history lesson so important today?
I mean, just look at this timeline. It really shows you how fast all of this happened. In 2012, AlexNet kicks the door open and proves deep learning is the future. Just 2 years later, VGGNet shows us the path forward is to go deep with simple parts. And then just 1 year after that, ResNet gives us the brilliant tool, that skip connection, to go as deep as we could ever want. It's wild.
And here is the most important takeaway. These models, they aren't just pages in a history book. They are the absolute bedrock of modern computer vision. When a company builds an app that can spot skin cancer from a photo, or when a social media filter finds your face in a picture, they're not starting from scratch. They are standing on the shoulders of giants. They're using a pre-trained VGGNet or ResNet and just fine-tuning it for their specific problem, exactly like the researchers did with the rice diseases. It's just incredible to think that these foundational ideas, discovered almost a decade ago, are still so central to the AI that we all use every single day. VGG's principle of going deep and ResNet's elegant shortcut were truly game-changing discoveries. It really makes you wonder, doesn't it? What's the next elegant shortcut that's going to unlock a leap forward we can't even imagine yet?